Okay, so we're taking on the topic of polar coordinates and polar equations. So what's going on here? Typically, when we view the Cartesian plane and we have a point, we describe it as having an x-coordinate, which is how far it went to the right, and a y-coordinate is how far it went up, and we describe this as xy. I can put the same point in the same plane and draw a ray to that point. Okay, or some sort of vector or ray. And now I have an angle measure theta, and I have a radius getting out to that point. And I could label that point r theta, and that would give me another way to represent these 2 points. So we have to figure out how to translate between these. So we want the translation from first polar to rectangular. Okay, so there's 2 formulas here. To get the x-coordinate, you need, well, let's take a look at this. This is going to be a right triangle here, right? So the x-coordinate is the adjacent side here. So if I take r times the cosine of theta, I should get the x-coordinate. And similarly, this side of the right triangle is the opposite. So this would be r times the sine of theta. So that's my method from going from polar to rectangular. Given the r and given the theta, r times cosine theta gives me x, r times sine theta will give me y. So let's make the transition going the other way. Okay, so the transition from rectangular to polar. Alright, so now you have an x and a y, right? And I want to know first the length of the radius, right? Well, if you kind of think this through, put that x and y on a circle, then that circle has to be x squared plus y squared is equal to r squared. So given the x and the y, I can find r by taking the square root of x squared plus y squared. So square the x, square the y, add them and take the square root, and you will get the radius. Okay, now the question is this, well, what's that angle measure? Well, if this is x and that's y, this is the opposite, that's the adjacent, so that means the tangent of theta should equal the opposite over the adjacent, which means that theta should be the inverse tangent of y over x. So now I have a way, given r and theta, to get x, given r and theta to get y, or given x and y to get r, or given x and y to get theta. So I can go back and forth between these 2 systems of measurement. So just kind of getting the idea of a polar equation. A polar equation tends to be written as r of theta is some function. Okay, so let's imagine some curve here. And what happens here is this dimension r1 is based on this theta 1. So this function gives me a rule for how far out r should be given the theta as I go around the circle. So it's basically what a polar equation is. So this gives me another way to take something. So like, for example, something like this can be written as a polar equation. Okay, it's really simple. R equals, well, let's see, whatever x is, right? So maybe like r equals 9 would be a polar equation. It's a constant equation. It gives me a circle with radius 9. This in rectangular would drastically fail the vertical line test, almost at every point except for 2, right? So not good in rectangular, but here it's just a really simple function. So this is one of the examples of why we use these polar equations. Okay, so recapping, going from our theta to xy, x is our cosine theta, y is our sine theta, and going from xy to our theta, r is square root of x squared plus y squared, and theta is the inverse tangent of y over x. And ultimately, we're going to get functions r theta that will look something like 2 cosine theta, so that when you put the theta in here, you know what the r length is. Alright, thank you.